This PowerPoint will develop the concepts of work and energy. It will include the various types of energy and the work that is done to change the energy state of an object. All of this involves the law of conservation of energy. You have heard energy cannot be created or destroyed. It only changes form. We will be looking at mechanical energy. Chemical, nuclear, etc. are not part of this discussion. The next few slides list the types of energy and the interactions of energy systems. No commentary on this slide. Work is done on objects to change the state of energy of an object. In this slide, the formula enables you to determine the work done by a force. Note that the cosine theta of the actual force gives you the component that is in the direction of the motion. Theta is the angle between the applied force and the direction of motion. The problems we will be doing will be involving constant forces, not variable ones. Note that the unit of energy is the joule. With the work formula from the previous slide, you see a more basic set of units to make up the joule is the newtons times the meter. Since the newton has fundamental units, the newton meter can be broken down further. Therefore, the fundamental units of the joule equals kilogram meter squared per second squared. This will be useful as we see other formulae that generate energy. See the next slide for an illustration of this information. Look at the forces acting on the box. Note that there is work done on the box, and that work changes the state of energy of the box. This idea fits from our discussion of circular motion. Since the centripetal force is perpendicular to the motion, it does not change the speed, so the kinetic energy stays the same, and therefore no change in the state of energy. For those of you who have taken a calculus course, this shows how the work done by a variable force can be determined, the area under the curve, or the integral of the function of force versus displacement. The ability to do work is very misleading. Since we are only discussing mechanical work, it applies here. This slide is another illustration of the slide showing the box on a friction surface. In that slide, the net force accelerates the box, so it has an increased velocity. Since kinetic energy equals 1/2 mv squared, the net force accelerates the bus. Here, the fundamental units from the kinetic energy formula equal those of work. No comments on this slide. See that the fundamental units for work and kinetic energy are the same, kilogram meter squared per second squared. The forms of potential energy will now be detailed. These are gravitational potential energy and spring or elastic potential energy. Potential energy is energy of position. Note that the hand is doing work against gravity, and you might think there is no work done because the net force is 0 if the hand brings it up at constant velocity. But because it is changing position, the object gains potential energy, and the work done against gravity results in a change of state. Choosing a position 0 is important. Where is the position 0 or ground position? Once you have chosen it, all potential energy is referenced from that point. One form of potential energy was gravitational. Now we will consider spring potential. Please refer to the handout I sent you entitled Spring Notes before you view this slide. The formula on this slide is Hooke's law. You will be doing a paper-pencil lab related to springs, Hooke's law, and spring potential. We have seen that energy has the unit of joules. The formula on this slide must lead to the fundamental units of joules, kilogram meter squared per second squared. As can be seen on the slide, this is true. The idea that energy transforms from one type to another is borne out by seeing all the types of energy we looked at have the same fundamental units. If you rub your hands together, what do you feel? They get warmer. Where does the energy lost by friction go? To another form. That form is heat. In the metric system, heat is measured in joules. So even though friction is a non-conservative force, the energy is not lost but transformed to heat. In this chapter, we will only see gravitational and elastic potential energies. If you take the next course, Physics 2, you will see that electric energy is also measured in joules. An example of Formula 610 would be an object sliding on a surface with friction and coming to rest. The change in kinetic energy equals the work done by friction. No comments on this slide. As the object changes position, the amount of potential energy and kinetic energy changes. The total energy remains constant. In order for this to have been done, some work must be done on the object. In this case, the work is done by the gravitational force acting on it. In this slide, you can see this relationship of work done by an outside force and changes in kinetic and potential energy. Here again, gravity does the work to speed the roller coaster up as it gets closer to the lowest point in its path, considered ground zero. As the roller coaster goes up the path and farther away from ground zero, gravity again does work. Note that the work gravity does first increases the kinetic energy and then decreases it. In this slide, the relationship between kinetic energy and spring potential is important. There will be several homework problems that will involve a compressed spring expanding and giving an object kinetic energy, or the spring removing kinetic energy when it is compressed. Again, the spring does work on the object to change the state of kinetic energy. This is the law of the conservation of energy, one of the three great conservation laws. We will encounter the second great conservation law in another chapter, the law of the conservation of momentum. No commentary on this slide. I have asked you to review example problems in the text. See example 6-12, which refers to the picture in slide 26, the roller coaster. It is set up like this slide in the presentation. Power adds in the time unit. It is a rate. It is a simple relationship. In this slide, the more fundamental quantities of work are used to see that power can be expressed in two different formulae. Hopefully, you are now an expert on this chapter.